The following slides give you some more detail about the FCN if you are interested in how it's set up all the kernel size, the try, the activation function. If you want, you can take a look. Okay, I won't give you any more details. After FCN, here comes SETNet, segmentation network. It's more symmetric now. See that? It's more symmetric, okay? Because in the original FCN, what you see just convolution, let's say, okay, followed by VGG, okay? But when you come to the second segmentation model called SETNet, you can see here's the encoder and decoder. But take a look again, okay? It is symmetric now, but it still go for what? Convolution, pooling. Convolution, pooling. S3 convolution and pooling. And again, it's a VGG. It's based on the VGG network, okay? And after that, for decoding is symmetric with respect to the encoder, okay? With respect to the encoder, okay? So then the red color represent upsampling, and then you do the convolution, okay? You use upsampling convolution. Actually, you can replace it with transpose convolution, not before, okay? But you need to do the upscale, okay? So usually it's supposed to work better than the FCN, but FCN is quite simple, right? So if you don't need the details, then FCN could be good enough, right? It's much easier, it's more easier to train. Okay, but anyway, now we have the encoder, decoder, and they are symmetric. Okay, they are symmetric. Okay, but for segmentation net, okay, they are not connected, but it's not like UNet, okay, the one you are going to see. The upsampling, you will see that you put the line here. That's because the up is based on I mentioned this before, right? Max pooling, unpooling, okay? You need to remember when you go for the max pooling, for this case here, you have to remember what okay, the size is 2 by 2. Then you have to memorize the location for the local maximum value. In this case, it's 0.8. So you need somewhere, okay, to memorize where is the maximum location, okay, for that. So the only connection here, it just show you how to do the upsampling based on the maximum pooling, okay, for it called it unpooling, okay, unpooling. So that, but actually it's different. The connection here is just to memorize the location for the local maximum pooling. That's it, okay. They are nothing to do with the attention, okay, or the so-called skip connection. Just try to memorize. You need somewhere to recode the location for each, okay. So when you do the upsampling, okay, when you're 13, I know I'm 13, I got to put it here. That's because it's based on this localization memory here, 13 is right here, and all the others you just fill with 0. That's it, okay. You don't need to use segmentation network because UNet perform better than that. Okay, so you can still use fully connected for some to make your computation fast. But for this one, I don't see no reason you need to add something from here. No. Okay. But anyway, that's how. But anyway, it is advanced, okay, to make the encoder and decoder symmetric, okay, and it use max pooling. Actually, you can replace it with interpolation, right, or another, or transpose convolution. Okay, here comes the unit. Okay, here comes the unit. The model here, we can divide it into half. So on the left, you can think of it as it's an encoder, okay? On the right, it is the decoder, that's it, okay? Just like the segmentation, exactly just like the segmentation network. They are basically the same. But you put it this way, that's why you call UNet, because it got the U shape, okay? But it does not have to be, okay, formula like this, okay? I mean, graphically, we just put it just like a U-shape structure. But basically, it's exactly like this. Now, the only difference is right here, okay? You made the connection, see that? You made the connection, layer by layer, okay? So first, the decoder and encoder are symmetric. They must symmetric. So that, and this is called, usually this is called skip connection. This is called skip connection. Okay, called skip connection. In UNet, the skip connection is given by concatenation. Okay, it's given by concatenation. The skip connection is given by concatenation. 它用串接. They don't add together. No. I mean, the concatenation means what? The output from here, we input, then we go for 2 convolution layer. Okay, we go for 2 convolution layer. The output is connected to the corresponding layer in the decoder, but we use concatenation. 就是我们把它串接在一起. So it will increase the depth. Okay, we will increase the depth. Let me say it again. We don't do the element-wise addition. 它不用加法，它只是把它串接. So which means what? If you go for this one, if you go for the architecture like this, as you know, when we go through a lot of convolution layer and maximum pooling, it will lose a lot of spatial information, right? The information you will lose. So the good thing about the UNet is what? No matter how deep it is, then you will do this concatenation or skip connection, which means you will put the original spatial information back into the decoder. Okay, we put it back to the decoder. And we allow the convolution here, or upsampling here, or transpose convolution here to learn the filter. Now we'll better get to make the segmentation result much closer to the ground truth. That's the idea, because otherwise, just like the set net, I mean, when the convolution, after a lot of layer of convolution and pooling, you will lose a lot of very detailed information. Okay, so the UNet about the good thing about the UNet is you will try to concatenate. Okay, so that you won't lose the spatial information preserved in the lower layer level. Okay, if you consider this as a higher level, okay, when you do the recover, so that's the idea. Okay, in the original, okay, UNet port, you use 64 by 2 convolution layer. The filter size is 64 and 64, and then we increase the number of filter, or you double the filter. Okay, 64 now becomes 128, now becomes 256, and then 512. You don't have to do that, okay, but that's the original model. Do the thing, okay, and then finally you do the flatten and put it back, okay, put it back. So you can see and then you put it back. You can see a white part here and blue part here. White parts mean what? The output from the decoder, okay? The white part from the decoder, the white part from the decoder. Okay, and the blue part means the convolution result, okay, from the decoder. That's it. So it carry out the concatenation, okay, not the addition. So that's exactly what. So the only difference here. So you know the training is very efficient. It's very efficient, and the implementation or the inference time is also very fast. Okay, and as you know, the base idea just a little bit just almost the same as VGG. Okay, to convolution layer to convolution layer. Okay, and the number of filter, it will be double in every layer, and you will transfer the output and concatenate with the output, okay, in the decoder. Okay, so that's it. That's the only. Very effective. Okay, very effective. Okay. So it still go for the maximum pooling with the default 2x2. Okay, and upsampling. That's it. Okay. The filter size is still small, 3x3. It uses red rule as an activation function, 2x2 mass pooling, okay, with a stretch of 2 to downsample. So after that, you will upsample by 2, okay, by a factor of 2. So that's it. Here, as I mentioned, just remember, you do the concatenation, 串接, 直接串接. Okay, so you will increase the depth. You will increase the depth after the concatenation. Here, the depth. Okay. The original UNet model, it has a total of 23 convolution layers for both encoder and decoder. Okay, encoder, decoder is up to 23. Okay, so that's it. Okay, that's all you need to know. Okay, so the breakthrough for segmentation network is it at the concatenation between each layer in the decoder, in the encoder, and the corresponding layer in the decoder. Okay? So that's it. So I just put further details. Suppose in the encoder you have the feature map is the size is R by C, but you have an E channel, and in the decoder the size, remember the size must be the same, otherwise you cannot do the concatenation. Okay, the size must be the same. And suppose the channel is D, so they don't have to be the same. Okay, so after the concatenation, the size will become still R by C, but the depth will be E cross D. Okay, I mean the channel, or the depth of the feature map. Okay, so that's it. So this figure just demonstrates. Okay, if this is the from encoder. The size is 16 by 16, but the depth is 32. Now, but after the convolution, the feature map, it got to be 16 by 16, but the channel is 24. After the concatenation, okay, the size is still 16 by 16, but the number channel will become 32 plus 24, okay, which will be 56. It's a good thing also to notice that this has nothing to do with the UNAP, but something to do with the concatenate. When you do your term project, I will encourage you to think of it. The input could be an image. The input is an image, and then we go for example, you might go for a CNN for feature extraction. But also, if you know something about this image, you can you can also input the vector value data. For example, you input depends on your application. You input a face image, but you might also input 0, K, and 50. For example, just for example, 0 could mean it's a female. It's a female, and 50 could be the ages, okay, of the person in the image. Then, because you can extract the features, right? You can extract a lot of features. Then you can concatenate, which means you can combine different types of the input data into one single representative vector by concatenation. 就是有时候在做，没有说影像，你其他有资料为什么不用就用？ Or even you might have the time series data. You can put them all together. Okay, that's another application, especially for the vector value data here. Okay, so that you can do the concatenation, and after that, then you can do further to reshape it into a two-dimensional, or then connect another CNN, or you can put it together, or then input it to a MLP model. Okay, multi-layer or fully connected layer. You can do a lot of things. So this is a good thing. You can combine unstructured data and structured data by concatenation. Okay. And put them and input to a single model for decision making, or for classification, or for regression, or for a lot of things. Okay. Maybe for this case, maybe then you can input more. Then you might estimate its salary, annual salary, in mind, just by looking at the face. or the is male or female, or the ages, or education level, okay, yeah, a college graduate, or a graduate student, or blah, blah, blah. And then you can provide more information. Then you can do a lot of estimation, okay? It sometimes could be better just to look at the image alone. Now, anyway, everything depends on your application, okay? So that's a good thing for this one. You can concatenate different types of data, okay? And about the upsampling, I already mentioned that when we talk about the autoencoder, okay? But just say it again, okay, nearest neighbor. I would recommend it if you want to select your own, just go for the bilinear or bicubic, okay? But it takes time, okay? Bilinear could be simple, or by the transpose convolution, okay? If you go for the strike by 2, if you go for the transpose convolution with a strike by 2, then you don't need upsampling. Because when you do the strike by 2, you will do the upsampling by a factor of 2. 好，这时候你只要用 transpose convolution 的话，你那个 strike 选2的话，它直接就会把那个影像放大。OK， OK。And here, DenseNet is another one. Based on my own experience, usually DenseNet will perform better than UNet, okay? In terms of the segmentation result, but it takes more computational time, okay? For the training and also for the inference. Basically, the original DenseNet is for classification. Okay, it's for classification. But later on, some researchers extended for segmentation. But when you take a look, it's kind of just like UNet. Okay, but the only difference here, it shows dB means dense block, okay, or DenseNet block. Okay, I will show you. And then you will do the concatenation, just like UNet, okay? Just like UNet. And here's the encoder, and here's the decoder, okay? So you will go for the dense block, okay? And here it do the transaction downward, and here's the transaction upward, okay, downward, upward, that's it. And the yellow one means concatenate exactly just like UNet, okay. So the only difference is right here, the dB, dense block, okay. Let's take a look of the dense block. Here, it shows you, this is just an example, okay, used in the original model. It does not have to be. But the growth rate is 4, okay? First, you determine your growth rate 4. It means I have, here's a 1, 2, 3, and 4, okay, 4. This is the feature map. It shows you different color. It's nothing but just show you the number of channel. For this case, it just assume the number of channel is 4. That's it. Okay, it doesn't matter. The growth rate 4 is based on x1, x2, x3, x4. So you can use only 2. It'll be fine, 4. Now, if you remember about the remember, residual net, you will bypass. Okay. Take it off here. This is the input. Okay, then you will go through batch normalization, rerule, and convolution, and output. Now, it's not the traditional way. Is output is connect to the next, okay, layer. Now, the output is not only to the next layer. The result here is connect to all the. See that? Can you see it? To all the convolution, batch normalization, rerule, convolution. 1, 2, 3, and 4. So it takes time. It's a little bit complicated. See that? Okay. But for your own application, sometimes you might use a growth rate of just 2, but this is a growth rate of 4. Okay. So anyway, you will connect to 1, okay, 2, 3, and then 4. And then after that, you will go for the next, okay, go for the next block. Okay, that's the only difference. That's the only difference. So the connection, you will, and for the remaining, for the convolution here, okay, for H2, see that? Then you will connect to the next, and then next, and the next one here. Okay, that's the only difference for the dense net. So it's more dense compared to the residual net, right? Okay, that's the only difference. And for classification, it has good performance, but later on, people just extend it for the encoder decoder. Okay, encoder decoder with the architecture line, just like this. Okay. Otherwise, they are pretty much the same as UNet. Okay, just like UNet, but for each block. So in UNet, this is just a convolution, right? But for this one, you need to go for all the connection. Okay, for all the following convolution. So in this case here, let me show you. Okay, now the concatenation will include, if xi is the input of layer I, then the input for the next layer will include all the previous output of x0, x1, and up to xi. That's what I'm saying. You need to do the concatenation for all previous layer. Okay, the output from all previous layer. Okay, so, but for residual net, it just go for something like this. It's different. So dense net is more computationally expensive. Okay, but the performance is better than UNet. Okay, the performance basically is better, but it's not, sometimes it's not that significant. Okay, so I just keep saying, if you only have one choice, just go for UNet. Just go for UNet. Okay, and then if you want to have a better performance, and you don't need to consider the real-time application, then DenseNet will be another good choice. Okay, and this is for classification or for regression. Okay, the input, then you go for the dense block. Okay, just like this. Okay, you need to concatenate from all previous convolution. Okay, that's it. So you can think of this as a convolution, but it contains all the skip connection and then finally fully connected. The output could be class or regression. It is a very pretty good effective example, okay? Model for you to use. It's not that popular because the training takes time, but it's still good and easy, understandable, and you can rewrite your own model. Okay, it's not that complicated. It's not that so complicated. Okay, so this is still it is ignored by a lot of researchers. I don't know. Okay, one of the reasons could be it's slow, especially for the residual net. Okay, if you go for use this one for another application, then you will slow down the training and the inference time. Okay, so that's it, and this is more detailed information in the dense net for segmentation. Okay, so that's it. Okay, and okay, finally, I still have 10 minutes, so let's talk about this. This is up-to-date version for segmentation, okay, for pure segmentation called DeepLab. The one I show you here has been updated to version 3, okay? I don't know if there's a version 4 or, but the one you show it's based on dilate. I prefer this word. It's much easier to understand instead of this word. Okay, dilate. You know, dilate. It's based on a dilate convolution. Okay, DeepLab. Now you can select the dilation rate. If this is the filter, okay, it's 3 by 3. You just follow the conventional convolution layer, okay, 3 by 3. Nothing special, just a convolution with a filter of 3 by 3. Now, but if the dilation rate is true, it means we insert one empty pixel between, okay, the column and the row. So now the original filter size is 3 by 3, now has been extended to what? 1, 2, 3, 4, 5. If you consider this one, then it might be 6. Okay? But the good thing about the dilation is what? Think of it. How many parameters for this filter you need to determine? 9. 3 by 3, 9. 你有9个变数. But if you extend it if you want to look wider of your neighborhood, so when you use no method for this one is 5 by 5, or let's assume it's 6 by 6. Then you need 36. You need 36 parameters to determine. But if you go for the dilation, how many parameters here? It's still 9, just 9. Even when you go for the dilation rate of 3, which means we insert 2 empty pixels between each column and each row. Now the size has become 1, 2, 3, 4, 5, 6, 7, 8, supposed to be 9. However, the number of parameters for this filter is still 9. We don't increase the number of decision variable. Everyone follow what I'm saying here? That's the good thing. But so with dilate convolution, you don't increase the number of parameters of the filter, but you have a wider observation view. Okay, right? because for this one you can just look for the neighbor, right? Just on your right, and on the top and the bottom. But for this one, you can look for, right, from 2 pixels from you. Okay, so this is called red 3 dilation, red 2 dilation, and red 1 dilation is the original convolution. That's it. Okay, that's how it goes. That's how Deep Lab apply this algorithm. Okay, for cementation. It means what? If it's good, if this can be help your cementation, it means what? We can look in not just a very small local area, right? We can look for in a wild area. So you can make decision. What should be the class for this very pixel? Okay? Based on its neighborhood. But not just a very small neighborhood. Instead, it could be look for a wild neighborhood. That's the idea. But without increasing the number of parameters to optimal. OK？ 好，所以基本上你假如用3乘3就是9个。那不管你的 dilation 用多大，它还是9个。可是它可以看的范围呢就比较广。可是，在做 cementation 的时候呢，不是只看，因为有时候你必须要看远一点，才知道它到底应该归属这个点应该归属什么样子的区域，会是有好处的。所以 so therefore the Deep Lab is some new model you can watch on, okay, especially for your cementation application. Okay, that's good. Now that's the basic idea, just for in the model here, it's nothing just like the CNN model. Okay, you go for the block. It can just like the VGG, but at the very end, here comes the equal ASPP. Okay, then it look for what? It look for 3. Okay, it look for 3 dilation scales. Okay, it used the rate of 6, 12, and 18. It's quite large, you know. It's quite large. In terms of the pixel, it look along is 18 pixels away. But if for a 3x3, it still maintain the number of parameters for each filter to be 9. But it can look for its neighbor, okay, with a rate of 4 and 12 and 18, okay. And also here, you must go for 1-by-1 convolution, okay, 1-by-1 convolution, which is the original, okay, the original input side. And then after that, you need to resize the shape and do the concatenation, okay, you just do the concatenation. And finally, go for 1-by-1 convolution. What is the purpose of 1-by-1 convolution? Just to reduce the number of channels. Okay, 因为你这边做了很多 right? You go for the dilution by a rate of 4, rate of 12, rate of 18. Okay, and also you have the pooling. When you put that all, concatenate all this together, then it will become very, very deep, right? Right. So the only purpose of 1-by-1 convolution is just to reduce the dimension. Okay, and then so the main contribution for Deep Lab is do the multiple dilate convolution, so that it can do for the local information and also in a more global information or wild neighborhood. Okay, so that the cementation could be better, just to look for its neighbor or 3x3 neighbor along. Okay, That's the purpose for that. Okay. So just keep saying basically the same thing here. Okay. For the decoder encoder, it proposed the original like the UNet, we had an image. It reduced the size by half. Okay, or by a factor of 2. Okay. And for the decoder, then we will upsample again by a factor of 2, and then we do the concatenation. Of course, for data, we can do the same thing here, but in the deep lab proposed architecture for segmentation, for the encoder, it almost the same as the UNet, right? We go for the convolution and reduce the size by half for each convolution, the same here. But almost at the end, it go for the pyramid pruning, okay? This is exactly the same, just like the one I just showed you here, okay? Then after that, see that it does not do the corresponding skip connection, but instead it just do it connect to, now it upgrade by 4, okay, upscale by 4, and then do the spatial skip connection or concatenation just right here, and then it upscale another 4 with a factor of 4. Then you reconstructed the expected segmentation, okay, image. That's it. So for the decoder in the deep lab, it's not symmetric. Okay, it's not symmetric. What I can say is the main contribution is right here. But after that, it still can go for the UNet. It doesn't matter, but apparently it's not necessary for the deep lab model. I didn't try it myself with every possible connection, but this is the model proposed. Okay, but the only thing you must keep in mind is just you can think of, you might go for the dilate a little bit, just like the inception. Remember inception? It parallelly do the convolution with a 3x3, 1x1, 5x5, and 7x7, right? But this is not. It uses the dilate, okay? Because if you go for the 3x3 filter, you need 9, okay, parameter. Then if you go for the 7x7, then you need a lot, right? 49, right? But when you go for the dilate, no matter what is the rate you use, and the number of parameter of a given filter, it doesn't change at all, but it can look a wider region. And supposedly it can give you a better local information and more global information at the same time, okay? And I believe with this approach, the computation time won't increase too much, okay? Because you only carry out in the end of the encoder, and then it do just 1 or 2 concatenation in the decoder. So I believe the payback is worthwhile, okay? Because computation time won't increase too much, but I believe the result could be better, okay? So anyway, here just try to re-emphasize it. It's a deep lab version 3, not just version 3 called version 3 plus, okay? So this is an up-to-date model I can find. Okay, so but basically they are the same as what I just mentioned here. Okay, so again here, okay, this the convolution. Okay, here's the dilate convolution. Okay. Okay. And after that, I just give you more information about the FCN. If you want to know, not quite understand what I'm talking about, just give you more information. But again, UNET is the best choice that you can have. Okay. If not, go for DanceNet, and you can also try out Diplet. Okay, Diplet. And that will be enough, especially for your cementation. Okay. But the only thing you need to worry about is you need manually annotate. Okay, you need to do the pixelwise annotation of the training images so that you can set up the ground truth. Okay, so that's it. Okay, that's about. Okay, and next week I will talk about the object detection. Okay, I'll talk about object detection, or you prefer talk about GAN first.
I think the object detection.
Okay, then I'll talk about the object detection first, and then
It will be contain the YOLO, right? You will talk about YOLO or not? YOLO.
but I will talk about mostly YOLO 4. Just YOLO 4. Okay, I will talk about YOLO 4 because there are too much details. If you want to cover the YOLO 7, YOLO 8, that will be too much. Okay, but with the knowledge on YOLO 4, that will be good enough for you to understand everything. Okay, YOLO 4 is developed by Liao Hongyan from the Central Silicon. Okay, 中央研究院 Okay. Okay, so and after that, and then we can go for the GL. Okay. Then we will be almost done with it. Okay. So anyway, work on your final term project. Okay, as soon as possible because you will have a final. Not today. You will have a final assignment. Okay. You have a final assignment. So you need to work on both the final assignment and your term project. So must go fast. Okay. And I did mention the presentation day will be on the final exam week. Okay, no written exam. Okay, so that's it. Okay, let's see you next week. Okay, object detection.